Okay, so we're going to talk about a slightly longer section today, 1.54 on inference and decision. It's a longer section, but I think there's some really important ideas here about how, our approach to decision problems. And there's actually one, I think, really quite profound and important figure that we'll discuss as well, which I thought was really cool. And yeah, I'm really excited to talk about it. Okay, so he starts by saying, so far the way we've been solving the problem is we've been starting with, we've been inferring the class of a particular data point. So we're given a data point, and we infer what class it belongs to. So for example, that was a photograph, and we guess whether the person has cancer or not. Or, for example, let's say you're a self-driving car, and you want to determine whether this pixelated image you have of I guess a scene in front of you contains a stop sign or not. So we first kind of assign the data to the class, and then we make a decision. But the question is, why do we do things like that? Why not, for example, in the case of the self-driving car, why not just go directly from the image to pressing the brakes? So why do we need to go build up the probabilities in between? And the important thing is that there's at least three ways of approaching this problem, and so we're going to talk about those three ways, and that's kind of what this whole section is about. So the very first one is kind of the most computationally intensive one, which is, so there'll first be an inference step, but instead of inferring the class, so what were we inferring before? We were inferring the class given the data point. Here we first infer we infer the probability of the data point given the class. So that would be like inferring the probability of that image of a stop sign, give that image, sorry, not the image of the stop sign, but the image that you see in front of you, given that it's supposed to come from a stop sign, pictures of stop signs. So you can kind of imagine that's actually kind of quite a difficult problem. How are you going to get the probability on every single pixel given just the class? So, but let's say you could do that. And then you could also infer the prior class probabilities. That's a bit easier to do because you can just kind of count how many, let's say, examples you have of each class. So once you have those pieces, then you can combine them using Bayes' rule. So here is now we're getting the posterior probability of the class given the data point, and we use our posterior on data. You could also think of that as a class likelihood. The class prior, and then the probability of the data point. I think that's called the marginal likelihood. I always forget that what this one is called. And the cool thing is that you can actually, given this particular probability, the probability of the data point given the class, you can actually get the marginal distribution of the data point, and that'll be important. We'll see in a second. But that's kind of a little thing you get for free that you don't get if you just work with the posterior probability. Okay. Equivalently, so this is all, you essentially have to do the same amount of work. You can just model the joint distribution of the data. So what is the probability of having, observing these pixels and it coming from a given class? And this is, not that much more work because this is just P of X given CK times P of CK. So, the amount of work is most of the work is in this thing, not that. So most of the work is going to be in getting the distribution of the probability of the data point given the class. So yeah. Now once we've got all these probabilities, then we just use decision theory as usual to determine the class membership. So the question is, why did we go through this whole step of of inferring the probability of data point given the class membership? And the cool thing about this is, and we'll talk about this in a second, the cool thing is that it'll allow you to actually sample from the distribution. So unlike the other approaches, you'll be able to actually sample, for example, images containing stop signs or images for the class where you're supposed to stop. And that can be really, really useful. And these days, generative AI, it's all about this, being able to generate, data points from a particular class. And now those classes are things that are much more complicated. These are, for example, prompts that you give the generative model, and it will generate you like a picture of an astronaut golfing on on Mars or whatever it is. So yeah, so this first approach, where you actually model this thing, they're called generative models because you can sample from them. So and maybe it's just worthwhile thinking about how you would do that. So for example, you would first, let's say you would sample from, stop signs. Actually, so let me go back. So the way you would generate kind of scenes here is first you would, let's just say objects. So you would sample an object from your prior on classes, and then once you do that, then you would just use this probability that you have to generate a instance of that class. And if you just kind of kept doing that, you would get different images showing up from each of the classes, showing up according to their prior probability. So you essentially be able to generate kind of your whole data set, or data set like the one you have. So that's kind of why they're called generative models, that you can generate from them. You won't be able to generate from the other types. The next type, which is kind of what we've been working on mostly, is you solve an inference problem, but it's a different inference problem. So again, we're solving an inference problem, but now we're determining just the posterior on the class memberships given the data point. And that's much easier, right? You can just imagine it, right? Going from the pixels of an image to whether they contain stop signs is much easier than going from the class being stop signs and trying to generate images from that. So it's just a much easier problem. So once we've inferred that, then we just use decision theory as before, just like we've been reading, to assign each new x to one of the classes. So that's this approach is called a discriminative. These are called discriminative models as opposed to generative models. And the last option is, well, okay, why again, why go through these probabilities at all? Why not just map it directly from the data points to the decision that you want to make? And in that setting, there would be no point for there would be no place the probabilities would appear. So the probabilities play no role. You're just learning a rule, going from pixels to pressing the brakes on your in your autonomous vehicle. So the question is, when would you use these different approaches, and why can it be useful to actually infer some of these probabilities? Okay, so let's go. He's going to kind of talk about the relative merits of these approaches, as he says. Okay, so approach A is the most. So this was a generative model one. It's the most demanding because it involves finding the joint distribution. Remember, so this thing, the joint distribution over both x and ck. So, and in many applications, x is going to have high dimensionality. So again, imagine that the data set of images, scenes that electric vehicle might see, an autonomous vehicle might see, a self-driving car, and then trying to generate not the probability of having to stop given the scene, but actually generating that scene itself. So those pixels, like imagine how difficult that is. So that's really really hard. So that's what he's talking about here. X will have high dimensionality. Consequently, we may need a large training set in order to determine the class conditional densities to reasonable accuracy. Okay, so yeah. But the class priors is usually not a problem because we can just count, the probability of having to stop is, the fraction of your data set that contains, stop signs versus the ones that contain go signs. So that's not such a big deal. So one advantage, he says, is that it does allow the marginal density of data to be determined. So remember that, now when we have the generative distribution, we have basically we have the joint distribution. And the joint distribution, you can compute everything you want from it. And in particular, you can compute the probability of data, of a data point. And why is that useful? Well, then you can tell that a particular data point might be quite unlikely. So the p of x might be quite low. And so this could be clearly useful for detecting outliers. Here's a data point that I haven't seen before, so I don't know what to do about it. You can kind of detect that when you're in the generative approach. But again, it's like it requires such can often require a lot of data. And maybe maybe you don't need the data for your particular task. So, and that's kind of what we come to next. So what if we only want to make classification decisions? So we don't care about generating data. We just want to make a decision given an observation. So in that setting, it can be wasteful indeed, of computational resources and excessively demanding of data. So you might need a lot of data to fill that high dimensional space to find the joint distribution when all we need is the posterior probabilities. Okay, so all we need is this. So why actually learn, the joint distribution of ck and x when all you need is the posterior distribution on the classes, and which can be directly opposed. So this is that's the whole point of this approach number B. And now he says, look, and this is where the really cool figure comes in. Indeed, the class conditional densities may contain a lot of structure that has little effect on the posterior probabilities as illustrated in this figure. So I'm actually going to highlight this. I'm going to underline this because I think it's, there's lots of structure that has little effect on the posterior probabilities. So let's go and talk about what that means, because I think it's a really, really important point. So here is the figure. Let me see if can I make things a bit smaller so you can see everything a little bit. Okay, so I'm going to make it a little bit smaller. So let me shrink. Okay, that's fine. Good enough. Okay. So let's talk about what that means. So here is a setting. So let's zoom in. I'll just zoom in a bit more. Okay. Yeah. So these are just the class densities. We don't need to know what the y-axis is. These are just the class densities here. Okay. So here is the probability of the data point given one of the classes, and the probability of data point given the other class. So if you're if you're building a generative model, you're going to need to know all of these wiggles, right? Because that's part of the game. You need to actually figure out what these every little bump in the shape, and that the fact this only has one bump. So for generative modeling, you need to know the full structure of your data. And look, it's already pretty complicated with one dimension. Imagine what it's like with thousands of dimensions. Okay, but the important thing is that if you just care about making a decision, all the structure might not actually matter, because the decision you want to make, for example, whether the point comes from class 1 or class 2, and in this setting we're going to assume the priors are the same, what that depends on is the ratio of this to that. So the ratio of this value to that value. And for example, in this whole region, the probability of data coming from class 2 is basically 0. So in this entire region, it's very, if you observe any data coming from here, it's very likely it's coming from class 1, regardless of the exact shape of that data set. So for example, the shape could be, I don't know, something else, like like this, I don't know, something like that, and it wouldn't matter. And the reason why is because, so let's scoot over here to these posterior probabilities on the classes. So the probability of C1 given X is equal to Px given C1 times PC1 over Px, right? And so you can see that, P of C1 given X over P of C2 given X, so the ratio, so, and they add up to 1, so the higher one is, the lower the other one is. That's just going to be P of X given C1 times P of C1 over P of X given C2 times P of C2. So now we've said in this particular example that these are the same, so we can cancel them out. So all that matters is this ratio. So it's the ratio that's actually determining the decision to whether to assign the point to class 1 or class 2. So the point is that all these wiggles don't really matter, because what you're doing is just dividing a big number by a very small one. And those wiggles are just going to show up as tiny fluctuations here, which don't really matter in terms of the decision you should be making. So I think that's a really, really important point, that and it really highlights the difference between generative and discriminative approaches. That you might not care about all of these like tiny little wiggles if all you care about is making a decision. And so you really need to know kind of which camp you're in and what application you're in. So that's just what I wanted to mention. I thought it was a really interesting and important point. So let's just get rid of this. Okay, cool. All right, so let's continue. So that's what that figure was about. The difference between generative and discriminative approaches. But now finally, if you in approach C, you even throw away those probabilities. Say, look, all I need to do is just figure out this crossing point. So that's all there is to making a distinction between class 1 and class 2. I actually don't care exactly what the probabilities are. All I need to know is whether I should press the brakes or the accelerator. So all I need to know is this particular line. So why even go to probabilities? I'll just learn that decision from data. So the question is why might that not be the best thing to do? So, and that's what he's going to talk about. So he's going to say, there are many powerful reasons for wanting to compute the posterior probabilities. So on the class, so he means these guys. Even if we subsequently, I think he means don't use them to make decisions. So you might want to make those. You might want to compute these no matter what. So and we're just going to go through them. So minimizing risk. So remember, a couple of sessions ago we talked about minimizing the, how to make decisions when you have this loss function. And so remember, the rule was, let me write that down. So remember we said the loss of assigning x to j is going to be the expected loss. So sorry, the expected loss. So that's going to be equal to sum on k. So these are all the other classes times this is a true class. This is our assigned class times p of ck given x. Okay, so that was the formula that we had. So averaging the loss based on the posterior probabilities. And so now it's clear that, look, if your loss matrix changes, then the decision you're going to make, so you're going to now want to assign x to the class where this value is minimized. Well, if your losses change, well, that's really easy. If you've got these posteriors, you just evaluate, you update those numbers, and you just minimize them over j, and it's trivial basically. So your situation changes, it's easy to update your decisions. But if you don't, if you just map directly from x to a decision, and your losses all of a sudden change, you have to go back and solve the classification problem. You have to start over basically. So that's going to be kind of really inefficient. So that's one reason. So we've also talked about the reject option. So that's, remember, when we are not sure about which classes something a data point belong to. So you can only really do that with the posterior probabilities. I suppose you could also train, like, you could probably train a third discriminant function to map things to the reject region. So I suppose you can still do that. So I don't know if this is still a really good I don't know if this is a very good reason, because I think you could actually manage the reject option with the discriminant approach as well. But anyway, it's very easy to do that if you have those posterior probabilities. I thought this is actually a pretty interesting example, kind of a more nuanced example of why you might also why these posteriors might be useful. So this is a setting where we're trying to classify X-ray images, saying whether someone has a particular disease or not. And this actually comes up a lot, where you have kind of unbalanced classes. So for example, in your data set, thankfully, let's say only 1 in every 1,000 of the data points that you have actually correspond to a cancer case. So now if you were to go and learn a model to classify images, well, the trivial model that just maps everything to saying no cancer, it would have 99.9% accuracy. So, and that would just be because your model is so unbalanced that it's just very easy on that data set to just get very high high accuracy by just classifying everything as normal. So and it would be kind of difficult to avoid that solution. So the approach that he talks about for addressing this here is, let's try a balanced data set. So let's say we could just go out and gather a data set where the two classes were equal. So now we get equal exposure to both. So now if we want to actually go out and make decisions with that, we have to compensate for the fact that we've modified our data set. So how do we do that? So I thought we'd kind of go through his procedure here. So let's say, so what he says is, okay, so he says, so suppose we used such a modified data set and found models for the posterior probabilities. So now we've got something like, we've got P of CK given X. And now we say, okay, so from Bayes' theorem, we see that the posterior probabilities are proportional to the prior probability. So this is just saying that this is proportional to X given CK times P of CK. Now the thing is that in this particular setting, we actually, the P of CKs that we use were actually modified. So let's call, we'll put a little, a bar over them, trying to indicate the fact that we used a modified, we use modified priors. So why don't we, so now he says, well, what we can do is, then once you've got this, like this particular prior, which is proportional to this product, what we'll do is we'll actually now divide this, so by P of CK, which we know, and then multiply it. So then multiply this whole thing. Oops, just realized you guys can't see this. So let me erase that. Okay, let's see. Let me adjust Okay. Let's see where you can see up until. I'm just gonna. That's even. Okay, so that seems to be the. Okay, so let's do the situation here. Yeah, so let's actually, maybe I can zoom in a bit and can I have a bit more space. Okay, yeah, great. Okay, so my boundary is now here. Okay, great. So what are we doing? So the idea is we're going to compute the posteriors on classes, but we're going to compute them. So we know that this is going to be proportional to, from Bayes' rule, P of x given ck times P of x. Okay? Oops. P of ck. Okay, but now the point is that we've kind of gone and created a balanced data set. So our P of ck's don't actually reflect the real distribution of the data. So actually our posterior itself won't reflect the real distribution. So let's put a bar over it by saying that, okay, to reflect the fact we've kind of modified the data set. So now he's suggesting that the way we can actually fix the problem, so actually come up with a posterior that reflects the true distribution of data, is we'll take this. So we'll take this product, and now we'll divide it by P of ck, and then we'll multiply this whole thing, multiply it by the true fractions. Okay, so we're going to have, let's say, kind of a slightly improved, and we'll now take the bar off. We'll say this is equal to our posteriors from that modified data set divided by the priors in the modified data set, which we have because we created the data set, and multiplied by the true priors. And then you might need to normalize this. So let's put a hat on it because it won't be normalized. It won't necessarily sum to 1. So then we'll just say, we can have one final step, which is equal to, this hat divided by the sum on k, p hat ck given x, just to make sure things normalize. So that's just basically a procedure for, in this setting, of you being able to take a balanced data set, getting a new balanced data set in a setting where your data is originally unbalanced, coming up with a posterior, adjusting that posterior to reflect the true priors on data, and then being able to use that true posterior that would be very hard to train on the original data set just because you have such an imbalanced situation. And you clearly can't do any of that without having these posteriors. So you see this, everything we've done here has just been based on having these posteriors around. Without them, you really can't do that. So let's zoom back out. I think everything is fine. Okay, terrific. So cannot be applied if you learn the discriminant function directly. So yeah, it's clearly we can't do that. That really required having the posteriors. And finally, kind of another cool reason why you might want to have posteriors is, let's say you have, you want to break the problem down into a bunch of, sub-problems and then combine the results. So for example, in this medical diagnosis setting, maybe we have blood tests and we have x-ray images and we want to somehow, combine that information. And it might be really easy to just have two systems, one that interprets the x-rays and one that interprets the blood data, and we want to kind of be able to combine that somehow. And if you have these posterior probabilities, we can actually do that. And so here's kind of one simple way, which is called naive Bayes. So let's make the assumption. So it works on the assumption that given the class that some data comes from, the probability of observing the X-ray data and the the imaging data are independent. They're conditionally independent. So not marginally independent. So we're the marginal distributions are not going to factorize. But actually, this is not a bad. I would say in this particular setting, it's not actually a bad assumption, because it says that, for example, given that a person has a particular disease, then the probability that their their X-ray results will be so and so, and their blood results will be so and so, they'll be independent of each other because that the dependency between them is already accounted for by conditioning on the fact that they have a disease. So normally there might be a correlation between them, because if you didn't know whether a person had a disease, maybe there'd be kind of a clustering of symptoms in the X-rays and the symptoms in the blood, that would show up together. But once I tell you that, okay, that cluster is actually, these are people who actually have a particular condition, then the probability of those types of, those test results are going to be independent. They're going to be conditionally independent. So this is kind of a very powerful assumption that you can make, and it really simplifies a lot of computations. And in some cases, not necessarily many cases, but in some cases, I actually think it is valid. But you'd have to determine that, talking to domain experts, etc. Okay, so now let's see how does that help. So let's zoom in here. So we've got, this is the probability we're interested in, the probability of having a disease given these two types of data. So now the very first thing we do is we just apply Bayes' rule, and we say, well, this is proportional to the probability of those two test results given the class times the probability of the class, the prior in the class. And now here's where our assumption comes in. So now we say this joint probability factorizes into a product of the individual probabilities, the probabilities of the different test results multiplied by the prior distribution. And now you can see, let's actually write that out. So P of xi given ck, so P of xi given ck is equal to P of ck given xi times P of xi divided by P of ck. And so is the other one, right? So P of xb given ck is just P of ck given xb, P of xb given P of ck. So now you see that we've got this one ck up here. Now we're going to end up dividing it by one c. Oops, let me switch to the laser. We've got this one ck up here. We end up dividing it by two ck. So now we end up getting two posterior probabilities on top and one prior probability on the bottom. So that's where that expression comes from. Let's erase all of this. Okay. So that's what that's about. So we can get the posterior probability on the two, given the two test results, can be related to the product of the posterior probabilities on the individual test results scaled by the prior, if we make this conditional independence assumption. And if that assumption is valid, then having those posteriors will allow you to kind of combine information. You can imagine how you can do this for if you had lots of different test results, you're going to end up getting P to the ck, I guess, to the n minus 1, whatever. But either way, what's going to matter is just you can just multiply the posterior. So that can be quite effective if if this hypothesis holds. Yeah, so this kind of assumption where you assume that the joint distributions can be factorized like this, it's called naive Bayes. So we'll hear more about that later on as we go. And just to reiterate that the joint distribution will typically not factorize. So that's when we don't condition on the disease or the health of the patient. So we're in that setting, we're kind of integrating all the data regardless of what their states are, and then you would get these kind of clusters showing up. But the point here is that, or these kind of correlations showing up. But the point is that under some settings, it might make sense to hypothesize the factorization, and if you can do that, life can simplify dramatically. Cool. So that was kind of a bit of a longer section, but I think a really interesting one. So I learned a lot going through it as well myself, and I've gone through it before, as you can tell from the different the yellow highlights. So I think yeah. So hope you found that interesting as well, and yeah, I guess I'll see you next time. Thank you.